Alright, so I'm going to show you a trick for solving a really specific differential equation at first, and then we'll pay attention to how the trick worked and turn it into a general technique for solving differential equations. So here's a differential equation, tx prime equals x over t plus 1 over t. And what I'm going to do first is convert it into this kind of form. So all first order differential equations can be written like this. That's like the definition of a first order differential equation, is like x prime equals and then something involving x and t. So let me get it into that format. So I'll divide both sides by t. So I get x prime equals x over t squared plus 1 over t squared. And if you were considering maybe integrating to try to solve this, get that out of your head. That's not going to work, right? If you have x prime t equals xt over t squared plus 1 over t squared, and you attempt to integrate both sides, maybe like this, I'm going to use s as the dummy variable there. Yeah, there's no trouble integrating the 1 over t squared. That just becomes sorry, something like that. Like that, sorry. But yes, the point is, when you do this, so yeah, here you get x of t minus x of 0. But there's no way you can solve for x of t and get an expression for what x of t is. It's never going to be isolated because you have this integral that has an x in it, and x is unknown. We're trying to solve for x, right? So integrating is just going to run you in circles, just like we discussed last time. If we want to be able to integrate to finish and solve, then, if you want to be able to just integrate with respect to t on both sides and finish, you need the right-hand side to involve t's only. The problem is this x here. Okay, but there is a way to make integrating still work. It's not to just integrate both sides with respect to t from this stage, but to try and get the x out of here. So let me show you how this works. So first, see if you can write the right-hand side here as a function of x alone times a function of t alone. So here's a function of x alone times a function of t alone. This is the right-hand side there. Now we can get rid of the x stuff by dividing by it and just move it over to the other side. Like this. And we are always allowed to do the same thing to both sides of the equation, so I'm going to integrate both sides with respect to t. Now there's no trouble on this side. When you take an antiderivative with respect to t, there's no trouble on this side. It's just minus 1 over t. But over here, plus c or whatever, but over here, you might be wondering, how does this help? So now there's suddenly this complicated thing. Well, let me use a different notation to write this, just to suggest something that might happen. So on the right-hand side, what I have is the integral 1 over x plus 1, and then x prime, let me write that as dx dt. And then this dt, this is telling me what is the variable of integration. So notice very carefully notice that I did this step very carefully, going from the original differential equation here to here. I didn't just stick this blue squiggly line in front. I stuck a blue squiggly line and this variable of integration. So it doesn't make sense to just put an integral symbol in front. You have to integrate with respect to something. And I have chosen the same thing to integrate with respect to on both sides, and that's t. So I ended up on the right side with something I can just directly compute an antiderivative for, and on the left side with this. And the notation looks very suggestive. You want to cancel these two, right? It feels like that shouldn't work, considering that this is the derivative of a certain function, while this is just actually part of the integral symbol, right? But the notation is designed so that it does work. So by this cancellation, what I mean is you end up with this, where the integral is now with respect to x. So before the integral was with respect to t, and let me write this less lazily, it used to be x of t plus 1 down here, and really we were just not writing the t. Now it really is just an x. And what happened from here to here, so these are equal, these integrals are the same thing. And what happened from here to here, or well, they're equal up to a constant, right? There's a plus c. But what happened from here to here is this change of variables from integral with respect to t to integral with respect to x. And of course, it's not really justified by this silly looking cancellation. That's not really what's going on. But it's justified by the way you can do change of variables when you're integrating. It's called U substitution when you study it in Math 3B. So when you learn about U substitution, usually you're talking about like integrals with respect to x, and then you turn it into an integral with respect to u, and you worry about du and dx. Here, instead of du and dx, it's dx and dt. So due to the rules of U substitution, you can do what is very tempting to do and simply cancel these symbols and end up with an integral with respect to x. All right, so let's summarize where we got to after all that is done. We got to integral 1 over x plus 1 dx equals integral 1 over t squared dt, and we already computed that, the last integral, it was this. And the first integral over here, the integral of 1 over x plus 1, that's going to be log x plus 1. So I'm almost there. So far I have this equality, this equals this. That is an implicit, I guess you could call it an implicit solution to the differential equation. To turn it into an explicit solution, I could solve for x. So let me exponentiate both sides. So x plus 1 equals e to the minus 1 over t plus c. And this is e to the minus 1 over t times e to the c. E to the c is just a constant, so let me just give that a name just to make it look prettier. Let me call that d. And then let me subtract the 1 to the other side. So there's my solution to the original differential equation. And let me just show you that if you have Mathematica, then you can check whether it's actually correct pretty easily. Okay, so here's my function, de to the minus 1 over t minus 1. So let me define that function. And in Mathematica, when you're defining a function, you need an underscore like that to indicate that this is going to be one of the inputs to the function. And I'm going to use a lowercase d. Sometimes capital letters are taken, reserved for other things. E to the minus 1 over t minus 1. Or I can write it in a more conventional exponential looking way. Like that. Then x prime of t I can compute by literally just writing x prime of t. So you see, and I can take more derivatives, x prime prime of t. So I don't have to actually compute these by hand. And let me now go go back. I forgot what the differential equation was. It was this. So let me check if this is actually satisfied. So I'll compute the left-hand side. That's t times x prime t. Let me delete this junk here. So t times x prime t is that. So that's what the left-hand side is when I plug in my proposed solution. And then for the right-hand side, that's x of t over t plus 1 over t. Those are different. That's not good. I must have made a mistake somewhere. Pretty sure those are different. Oh no, I'm just not looking carefully enough. They are the same, I think. So how about I simplify afterwards? Yes, they are the same. There's the left-hand side and there's the right-hand side. Okay. So this is indeed a solution. Okay, so let's step back and think about what happened. If you just write it as, if you take the original differential equation and you just write it in this format, x prime equals some stuff, then you end up with something that you cannot necessarily integrate both sides to resolve, or to let u solve for x. However, we were able to split up the right-hand side as a product. So some stuff involving x only times some stuff involving t only. So this step is called separating. So we were able to separate the differential equation. So now it's separated. Then we could divide both sides by the stuff that involves x, and we ended up with, before we put these blue integral symbols on here, we ended up with stuff involving x times x prime equals stuff involving t. Then the integration worked, and it worked due to this this integral with respect to t turning into an integral with respect to x, and then the rest was algebra. So that's the example. Let's talk about how to do it in general. When we do it in general, we can only do it when this green step here is possible. So we can only do it when it's possible to separate